I'm Dr. Harry Cliff. I'm a particle physicist at the University of Cambridge, and I'm also a populariser of science and science writer. Welcome to my exp. There are a load of really big mysteries in particle physics, in fundamental physics in general, that we cannot answer at the moment. And this is why we do experiments at the Large Hadron Collider and also elsewhere. So I don't know whether there's a single biggest problem, but let me give you a flavour of some of them. So perhaps the easiest to understand is the mystery of dark matter. So we know from astronomy that there is about 5 times more invisible dark matter in the universe than there is ordinary matter. So by ordinary matter, I mean stuff made of atoms, stuff made of the particles in the standard model of particle physics. So this includes gas and dust and stars, planets, people. All of that represents only about a sixth or so of the total matter content of the universe. 85% of the matter in the universe is this mysterious stuff called dark matter, which is dark because it's invisible. It doesn't interact with light, it doesn't reflect, emit, or absorb light. So we can tell it's there from its gravitational influence on the visible universe, but we have no idea what it's made from. And there are no particles in nature that can explain what dark matter is. And one of the big hopes is that either at the LHC or at some other direct detection experiments underground, we might get a clue to what the particle of dark matter is. The Higgs boson is this particle that is related to the reason that fundamental particles have mass. Discovering the Higgs boson proves the existence of something called the Higgs field, which is an invisible field that is all around us, fills the whole universe. But the big problem with the Higgs field is this. Basically, the Higgs field is responsible for giving mass to the particles in nature. And the strength of the Higgs field determines how heavy particles are. So if you make the Higgs field stronger, particles get more massive. If you make it weaker, particles get less massive. But our theories suggest that the Higgs field should really have only one of 2 values. Either it should be off everywhere in the universe, i.e. have a 0 value. And if that were true, the particles that we're made of would have no mass and atoms couldn't form and we wouldn't exist. The other option is the Higgs field has an enormous value, technically a value known as the Planck energy, which is an incredibly high amount of energy. And if the Higgs field were that strong, every particle that we know about would become so heavy that the whole universe, everything in the universe, would collapse into a black hole, and you'd have a universe full of black holes and not much else. And we find in our universe, based on the experiments we've done and the theoretical understanding, the Higgs field has this value that is not 0, but is also not this crazy Planck value. It's just above 0. And this value seems to be incredibly delicately balanced in order to create atoms and structure and the things that we see in the universe around us. There's this big mystery. Why is the Higgs field set at this really weird, very finely tuned position? And the explanation for this, theoretically, there have been various ideas. There's one idea called supersymmetry, which is a new sort of symmetry in nature where every particle we know about gets a super version, a sort of super partner. And one of the big goals of the LHC was to find these super particles, but so far we've seen no sign of them. Some of the ideas you hear mentioned in fundamental physics and particle physics and cosmology do sound a bit like something out of science fiction. So one of these ideas is something known as the multiverse, which is the idea that there are many universes, not just our own. And this is sort of hypothesized to explain various weird features of our universe. Like, for example, that it appears that in many ways the laws of nature are very finely tuned to allow atoms to form and therefore for living things to form. And one way of explaining this is to say, well, maybe there are many, many universes where all the laws of nature are different and we only live in the universe we do because it's one of the few where the conditions are right for life. And that's not the only sort of sci-fi idea. Now, I mean, I'm a big fan of sci-fi. I enjoy science fiction. But I think my view, at least in science, is you have to go where you can actually make measurements, where you can get real evidence. And there is a tendency, I think, in the discourse around sort of the public discourse around science to focus on some of these really out there ideas like the multiverse. And while they're interesting ideas to talk about and play with theoretically, at the moment, at least, they're not grounded in experimental fact. And it's quite hard to see in some of these cases how you would ever perform a measurement or an observation that would tell you anything about these really hypothetical ideas. Particle physics, I think, does touch on these big philosophical questions. How did the universe come into existence? Why is there something rather than nothing, for example? Some of these questions possibly are actually beyond the realms of science, but if we're going to have any chance of answering them, then doing these sorts of experiments that allow us to understand the physics of the very earliest moments of our universe is the best shot we have of really figuring those things out. It may be that there's some limit on our ability to ultimately understand the origins of everything, and there are reasons for thinking there may well be limits on what we can know. But there's still a long way to go and a lot more to discover. So we may get more clues to answer some of these big philosophical questions. And there's definitely a resonance, I think, between those philosophical questions and the sorts of questions that we are asking in fundamental physics.